Hello and welcome to another lecture on microelectronics. In today's lecture, we'll be finding the Thevenin equivalent of this circuit shown here. The Thevenin theorem says that if you have a linear one-port network, then insofar as the output current is concerned, this one port can be represented in terms of a voltage source V Thevenin in series with a resistance R Thevenin. So if I consider these two terminals as the output where the load RL is connected and everything to the left as a black box, then I can apply Thevenin's theorem here and calculate the resistance looking back into the network and make a Thevenin equivalent circuit of this network. Now in order to find V Thevenin, we have to find the voltage appearing at these terminals due to this one port. So in our case, what is the voltage that appears at this point due to this network? So we have to find basically the voltage across RL. So we see from this circuit that one of the terminals of R pi is connected to this point here and the other one is grounded. So if I redraw this circuit, I have R pi which is connected to V in, and the polarity of V pi is positive where it is connected to V in. It's with this polarity V pi, and then we have the rest of the circuit. So from here we simply see that V pi is equal to V in. So since V pi is equal to Vn, this current generator I1 can be written as Gm times V in, and then if we apply KCL at this output node, then we can write that Gm times V in, which is this current, plus V out over RL, which is the current through the load, should be equal to 0. And from here we find V out as minus Gm times RL times Vn. So this is our Thevenin's voltage. We have found the voltage across the terminals of RL, which is minus Gm times RL times Vn. Next we have to find out the Thevenin's equivalent resistance looking back into the network. For that, what we do is that we connect a voltage source Vx which pumps a current Ix into the network, and then we find R Thevenin as Vx over Ix under the condition that sources are turned off. So V in is an independent voltage source, so this goes to 0, which means that we have a short here to ground. We cannot open this current source because this is a dependent current source which is depending on the voltage V pi. However, if you see, if I have a short circuit here, then this resistance also gets short circuit because this point is also connected to ground, and thus we have a short here, and thus V pi becomes 0, and now we can set Gm V pi is 0, so the current source becomes open. So Vx by Ix is simply, so Ix is simply the current flowing through RL, and thus Vx over Ix is equal to the load resistance RL. So now we can make our Thevenin equivalent circuit where the Thevenin equivalent voltage V Thevenin is equal to minus Gm times RL times V in, V Thevenin in series with R Thevenin, which is RL, this is the Thevenin's equivalent circuit. So that's it for today's lecture. See you in another lecture in the future. Thank you. Goodbye.